Hello, in this video we're going to talk about simulating continuous time models. So we'll start off with a differential equation. We're talking about differential equations of the form dx dt, and whatever that equals, whatever that differential equation is, we'll call that expression there g of x. So to approximate dx dt, we know that the dx dt is approximated by delta x delta t, and delta x is simply the change in x. So we could consider x of t plus delta t minus x of t. So it's just a difference in two x values divided by delta t. In other words, g of x is approximately x of t plus delta t minus x of t, all divided by delta t. If we multiply both sides by delta t, we get g of x times delta t is approximately x of t plus delta t minus x of t. And then bringing over, adding to both sides that x of t, we get g of x delta t plus x of t. That's approximately x of t plus delta t. This brings us to something called Euler's forward method, and the method says that if you want to know what the new x is, you take the old x and add to it some amount of change. And how do we get that amount of change? Well, that's really our g of x. That's our derivative, right? It's a derivative. It's a rate of change times t. So that cancels out the t and tells you how much to add on to x to get your new x. So let's implement that with the logistic growth model. This is a continuous logistic growth model, so it's a differential equation, and we're going to use Euler's forward method. So as a reminder, that differential equation, that expression there, that is our g of x. So here's Euler's method, and we've substituted in g of x for the logistic growth model. And in MATLAB, we're going to choose particular parameters so that we make a code that's very similar to Sayama's code 6.1. Okay, so I'm over here in MATLAB, and in MATLAB, we have put in the particular parameters of interest. Now I have another line here, line 12, which I'd like to talk about. This says t equals 1 up to time steps in increments of dt. Okay, what does that mean? Well, let's run these first couple lines of code, see what happens. So notice that we get a variable called t, and t is, if we take a look at it, it's pretty long. It's one row by 4,901 columns, and it ends off at 50, which is what we wanted. And where does it start? If we look at the first couple entries of t, okay, there's columns 1 through 8. It starts at 1, and it's incrementing up in chunks of dt, which is currently set to 0.01. All right, so that's what that line does, and that's going to be really helpful for when we go to plot, because we're ultimately taking x and we're going to increment it, and we're going to evaluate x at each of those little time spots, right? It's a very small mesh size. It's not just like we're evaluating at time equals 1 and time equals 2. We're discretizing time, and we're looking at very small little intervals of time here. So we're going to evaluate x at all those points, so we also need to keep track of the time at all those little points so that we can plot t and x. All right, so there's our for loop, and we've made a plot, t on the horizontal and x on the vertical axis, and let's see what the code does. So there's our plot, and the only thing we might want to adjust here is maybe set that vertical axis so it starts at 0. So you can go in here and edit axis properties, and we'll make that a 0. The reason why we want to start that at 0 is because if we don't do that, it could have a deceiving graph. So that looks much better, and then you could save the plot or do whatever you want at this point.